Hey hackers, the Coding Kid here. As you can hear, my voice is breaking. Bear with me please. A few days ago I tried to solve the Knight's Tour, a puzzle about a knight on a chessboard. The goal is simple: move the knight to every square without going to the same square twice. I tried to solve it myself. My first strategy was to go from left to right. I was careful not to miss any squares, but at the end I got stuck in the bottom right corner. I scored 58 squares out of 64. My next strategy was to go in a circle. Unfortunately, I got stuck after only 30 moves. My best score was 62, which I got by visiting the edges first and then coming into the middle. Near the end, I thought that I had done it, but I ran out of space. After that, I thought it might be faster to just code it. I decided to use P5.js to visualize the tour. I wrote the HTML, the CSS, and the rendering code in P5.js to draw the squares and animate the Knight's Tour. That was straightforward. The hard part is the function to solve the tour. To do that, we first need a square class, which just has a row and a column. The getMoves method returns all the legal knight moves from the current square. The isValid method is just a helper method to figure out which moves are legal. I'll start with an array of squares that holds all the moves of the knight. Initially, the array will contain one random square, which is the starting square. I'll use recursion to build the array until we have 64 legal moves. Now for the hard part, the recursive function to solve the tour. So, function solve, and it'll take in one parameter, path, which we'll modify in place. We'll want to return true if we're finished, so we can check if path.length equals 64, which is the number of squares on a chessboard, we can return true. And next, let's get a list of all the available squares the knight can move to. So const moves is assigned to path of path.length minus 1, which is the last square, dot get moves path. And now let's loop over moves. We can't use a for each loop because we might return inside of that loop. So instead, I'll use a normal for loop using I. Let's call path.push with move so that we add the move to the path. And now let's see if this is a valid branch by calling solve path. Now this will recurse, and if it finds a successful solution, in which case path.length will be 64, it will return true. And so we should also return true, and it will keep going up the call stack until the first solve function returns true. Okay, otherwise we'll call path.pop because we want to remove the move that we just pushed. If we haven't returned true, then we want to return false. Let's run that.
Approximately 10 hours later.
Okay, that was super slow. It took a very long time for the recursion to find a solution, but the solution was correct. Let's see if we can find a way to make it faster. Warnsdorff's rule looks interesting. All we need to do to implement it is to sort path so that we prioritize moves that have less onward moves. So we can do that using path.sort, which will take in two parameters, a and b, and we'll return a.getMoves path, which gets a list of the valid onward moves square A has, .length minus the same thing for b, b.getMoves path.length, which is the number of onward moves b has. Let's run that. That was amazing. It took just a split second to calculate the path using Warnsdorff's rule. Cool, we did it, and it was more fun than solving it manually. As usual, I've added the code to my GitHub, and you can have a look at a prettier version of this project on my website. Links in the description below. Thanks for watching. See you in the next one.